There is the lecture on third experiment, that is the propagation modes, wavelength and phase velocity in waveguide. So the objective of this experiment is to learn the theory of waveguides and experiment the propagation characteristics of microwave in free space as well as in a waveguide. Okay. So as the theory forwards, so the microwave waveguide is a hollow metallic pipe having rectangular or circular cross section, and this kind of waveguides has been taught in the many lectures of the theory. That you can see that the waveguide is a hollow metallic pipe that can be sized in rectangular shape or circular cross sectional shape. Uh, so these kind of shapes it comes forward, and the rectangular waveguides are used in our experiments. We are not using the circular waveguides in these experiments, and our mathematical analysis are based on the rectangular waveguides. So first of all, that is the reduced wave equation of rectangular waveguide calculation, and that is the for perfect dielectric the k square will be omega square mu epsilon, and that's the permittivity mu, and epsilon is the mu is the permeability, epsilon is the permittivity, and omega is the angular frequency. In rectangular coordinate system it becomes like that. Just change it in the rectangular coordinate. The rectangular coordinate system is established in this case such that z is the direction of the propagation as shown in the figure 3.1. That is the rectangular waveguide in rectangular coordinate system. And there is an input wave, as you can see, it's a transverse wave that has been put onto it, and that goes to the z direction. So our goal is not to obtain the solution which has a form of like that, the gx, y, f, z, but after solving the equation we get this equation, that is the last equation of that, that is the equation of phi, the separation of variable method. We get the phi, that means the flux, electric flux of that is the final equation. And the wave propagation in the positive z direction is represented at e to the power minus z beta j g z, and therefore e to the power j beta j z corresponds to our corresponding negative direction. That means as you can see that that is the after make a solution with the separation of variable, we get the equation like that. But there is a part of equation, in that part, whether the epsilon is there, that depends the propagation of that wave, that which direction it propagates, and the propagation constants are going through to it. But in the previous in the other multiples like a1, a2 and b1, b2, they are related to the magnitude. Okay, because in x and y direction, that means if it's a rectangular if it's a rectangular waveguide, it's a rectangle. So x represents some width or breadth, and y represents the height of the or length, sorry, x represents length and y represents the breadth of that rectangular hollow shape, and z is the path that the rectangular that the wave go through to the rectangular waveguide. And for this there is a phasor form of that particular waveguide has been situated here, has been shown here as c1 e to the power minus j. The minus j means that is the forward towards the z positive direction, and plus means that will go through to the negative direction of j. Okay, so let us go through to the next part, that what are the modes. As you can see that there are three modes particularly we taught in the microwave engineering. First mode is TEM mode, that is the transverse electromagnetic mode. Second is the transverse electric modes, or H modes, popularly known as H modes. And third is the TM mode, transverse magnetic modes, and popularly known as the E modes. In these modes no magnetic field exists in the z direction, however electric field does exist in the z direction. That means in TEM mode both electric and magnetic fields are transverse in the direction of propagation. What is known as transverse? Okay, uh, just think it is a three-dimensional. Uh, just think about the three-dimensional axis here. That is an x-axis, that is a y-axis, and that's the z-axis. Okay, so transverse means that is parallel to x. If it is parallel to x, that will be a transverse wave like in that portion, and that will go through to the z direction. And there are another thing that is like that is parallel to the y axis. But if you consider x as the electric field and y as the magnetic field, and both are transverse in the direction of propagation, just like it will just propagate like this packet, just this packet, if it propagates like a packet like this and go through the z direction that way, so that is TEM or transverse electromagnetic mode. The TE mode is known as the H mode. There will be no electric field exists in the z direction. However, magnetic field does exist in the z direction. Okay, so if we just think about that, if we consider that is the magnetic field, just magnetic field will go through to the z direction, so that will be transverse electric field, no field required for the electric field. But TM means transverse magnetic, whether there will be no magnetic field exists in the z direction, but the the electric field will go through to the z direction, just like that. So however, electric field does exist in the z direction. All the field components therefore may be derived from the axial component Ez of magnetic field. Okay, now going to the next section part, that is some TEM modes, TE modes for rectangular waveguide, and that is the popular example of TMN mode equation. And after calculating and solving it within the boundary condition, we find out that, and there are some wave equations out of that, and last of all the final form is Hz. That means the magnetic field in the z direction, that is TE, means there will be magnetic field but no electric field, so that will be in that form. And that is the amplitude, and here you can see N and M. That is the M, and M is known as the number of the mode. As you can say, if it is T01, T10 or T11, so M and N will be counted for that particular portion. TMN means there are some numbers, there are different type of modes and different type of numbers on it. And A is the length of the rectangle, and B is the width of the rectangle. That means that depends on the size and parameter of a rectangular waveguide. And e to the power minus j beta gz is the propagation constant, and propagation as you can say that depends on the propagation, how much it will propagate, in which direction it will propagate. The total propagation characteristics is dependent on the e to the power minus j beta gz part. Now after getting this, that is the four other equations on the x and y directions, and we get the value of that is the electric field x and y direction, and the magnetic field in z and y direction, as you can find it out. So after that, the long equation characteristics TM modes, and that is the TM mode characteristics. And after calculating the TE and TM mode, we finally get this thing, that is the cutoff wavelength, that is 2 divided by root over n by a whole square, plus it will be plus m by b whole square. That should have to be plus here. So that is gonna be the important part in that theory, that we should measure by measuring the power and other things. So that's for now, for the third experiment.